For today, our topic will be non-homogeneous differential equation with constant coefficient solution by variation of parameters. So, we study two methods that carry no such restrictions. In fact, much of what we do will be applicable to linear equations with variable coefficients. We begin with a procedure by D'Alembert that is often called the method of reduction of order. Consider the general second-order linear equation y double prime plus py prime plus qy is equals to r. Suppose that we know a solution y is equals to y1 of the corresponding homogeneous equation, which is y double prime plus py prime plus qy is equals to r. And then we introduce the new independent variable v by the substitution, which is y is equals to y1 v. Lead to a solution of equation 1, which is y prime is equals to y1 v plus y prime 1 v, y1 prime v, this is equation 1, and equation 3, which is y double prime is equals to y1 v double prime plus 2y prime 1 v prime plus y double prime 1 v. Substitution of 3 into 1, which yields to y1 v prime plus 2y1 prime plus py1 quantity v prime plus quantity y1 double prime plus py1 prime plus qy1 quantity v is equals to r. But y is equals to y1 is a solution of 2. That is y double prime 1 plus py1 prime plus qy1 is equals to 0. And equation 4 reduces to y1 v prime plus 2y1 prime plus py1 quantity v prime is equals to r. And then now let v is equals to y. So equation 5 becomes y1 w prime plus 2y1 prime plus py1 quantity w is equals to r. A linear equation of first order in w. By the usual method, the integrating factor, we can find w from 6, and then we can get v from v prime is equals to w by an integration. Finally, y is equals to y1 v. Note that the method is not restricted to equations with constant coefficients, and it depends only upon our knowing a single non-zero solution of equation. For particular purposes, the method depends also upon our being able to effect the integrations. So we move to our example number 1. Our first problem, we need to solve the equation y double prime minus y is equals to e raised to x. So the complementary function, we all know that yc is equals to c1 e raised to x plus c2 e raised to negative x. We shall take the particular solution e raised to x and use the method of reduction order by setting y is equals to v e raised to x. And then we move to y prime is equals to v e raised to x plus v prime e raised to x, and then y double prime is equals to v e raised to x plus 2v prime e raised to x plus v double prime e raised to x. Substituting into equation gives the formula or the equation of v double prime plus 2v prime is equals to 1. Equation 8 is a first order linear equation in the variable v prime. Applying the integrating factor, e raised to 2x yields so e2x so it yields e2x quantity v double prime plus 2v prime is equals to e raised to 2x. Thus, e2x v prime is equals to 1/2 of e raised to x plus c, where c is an arbitrary constant. So equation 9 readily gives this will be this will be equation 8. So where are we? Where c is the arbitrary constant, and so equation 9 readily gives v is equals to 1/2 plus c e raised to negative 2x. So this will be equation 9. And hence, v is equals to c1e raised to negative 2x plus c2 plus 1/2 x. So, where c1 and c2 are arbitrary constants, remembering that y is equals to v e raised to x, we finally have y is equals to c1 e raised to negative x plus c2 e raised to positive x plus 1/2 xe. So for our next example, we have quantity d, 2 plus 1 y is equals to cosecant x. So the complementary function of this equation will be c1 cosine of x plus c2 sine of x. So we may use any special case as the y1 in the theory above. So let us then put y is equals to v sine x. And then we find that y prime is equals to v prime sine x plus v cosine x and so y double prime is equals to v double prime sine x plus 2v prime cosine x minus v sine x. The equation for v is, so equation for v will be v prime double prime sine x plus 2v prime cosine x is equals to cosecant x, or v double prime plus 2v prime cotangent x is equals to cosecant 2 raised to 2 x. So we put v prime is equals to w, then the equation becomes w prime plus 2w cotangent x is equals to cosecant 2 raised to 2 over x, for which an integrating factor is sine raised to 2x. Thus, sine 2x dw plus 2w sine x cosine x dx is equals to dx. So we will get, from that, we will get w sine raised to 2 x is equals to x. And if we seek only a particular solution, we will have, so particular solution we will have w is equals to x cosecant raised to 2x, or v prime is equals to x cosecant to raised to 2x. Hence, integrating it by v is equals to x cosecant raised to 2. Oh, sorry. So again, so particulars from we seek only a particular solution, so we will have w is equals to x cosecant raised to 2x, or v prime is equals to x cosecant 2x. Hence, v is equals to, so we integrate it, so v is equals to x cosecant 2x dx, or v is equals to negative x cotangent x plus ln sine of x. A result is easily obtained using integration by parts. Now y is equals to v sine x, y is equals to v sine x. So the particular solution will which we sought is yp is equals to negative x cosecant x plus sine x ln sine x. Okay, wait, I'll turn the light. Okay, there. So finally, we will end into a solution y. Oh wait, I'll write it here. So finally, we will end into a solution y is equals to c1 cos sine x plus c2 sine x minus cosine x plus sine x ln sine x. That's it.